All right, students, I just decided to do a new video on the kinematics derivations. Now, as you can see, here are the equations that we went over in class, and as we've pointed out in class, they used V0 when it should have been, I really wish they would not do that. I wish they'd stick with their text. That should say initial, final, and that's final x, of course. And these are all in the x direction. That's why that x is on there. Initial, final, initial, final, initial, final minus initial, initial plus final, and that x, of course, means in the x direction, okay? And, of course, final and initial here, okay? That's subscript x right there, okay? That right there means in the x direction, in the x direction, in the x direction, okay? X direction, okay? So don't let that throw you off, okay? All right, so how do we derive the kinematics? Okay, well, if you go back to our previous discussions where we looked at average velocity, and if you recall that the average velocity is the change in displacement divided by the change in the time interval, okay? So if we were to plot this graphically, okay, velocity versus time, and we were to plot this, well, we know, and let's say we were to have an initial velocity at this point. If we were to have constant velocity, we know that the line would look like this on a velocity versus time graph. However, if we have an initial velocity, VI, and we go to a given point to where we have a final velocity, V final, all right, notice what we have formed here. Okay, we formed two geometric shapes. We have formed a rectangle and we have formed a right triangle. Okay, here is our right triangle. All right, now, so having said and done this, we can start to do some derivation. Now, how can we derive displacement from this equation or from this graph? Well, if you recall from this formula right here, if we solve for displacement, change in displacement is equal to the velocity, and yes, it can be average times the change in time, or just velocity times time. Okay, and we'll use initial just to keep for the sake of argument, because here's our initial velocity. So that means this area right here, if we multiply the velocity, okay, the initial velocity, okay, right here, times the time across the x-axis, then we get delta x, correct? So this is equal to the change in displacement. The area under that flat line, that horizontal line, should equal the change in displacement, because when you multiply velocity times time, you get displacement. Meters per second times second gives you meters, okay? All right, let's go a little further. Okay, so we know that. Let's look at our next graph. Well, we have a right triangle, and we know that the area of a right triangle, okay, area of a right triangle is 1/2 the base times the height. We know that, okay? So let's take this and let's look at this. So we have 1/2 the base times the height, okay? Well, what is the base? Well, the base is time. But what is the height, okay? The height is what? final, okay, minus initial. V final minus V initial. Okay. Now, and of course we know the bottom part of this graph, when we multiply velocity times time, that's delta x. Okay, but where is acceleration? Okay, so let's go ahead and write the equation. Delta x is equal to, all right, now let's look at this. Well, I tell you what, let me show you this equation right here. If you recall from our acceleration equation, when we looked at acceleration average, we said it was what? We said it was the change in velocity minus, or the change in velocity, or VF minus VI over delta T, if everyone remembers this correctly. And so if we set acceleration delta T is equal to VF minus VI. Let me move that. It's kind of getting crammed in there, okay? Okay. So acceleration times time would be equal to VF minus VI. Okay, well, do we see anything in this equation that matches this equation and we can do a substitution? We most certainly do. So what we can do is substitute what VF minus VI is equal to, which is AT, and what do we come up with? We come up with 1/2 AT squared. Because when you multiply A times T times delta T, or T, and that should be delta T, T delta T, we're not going to get all messed up. I'll go ahead and keep it delta T to keep all of you happy. Okay. Time will always be measured, typically when we're looking at change in time. There we go. Okay. So when we multiply those together, what do we get? Okay. Delta T squared. So our equation then is what? This kinematic would be what? Well, how do we find displacement? Displacement is equal to the initial velocity times the time plus the upper part of the graph, 1/2 AT squared. And of course, this is for constant. All of these are acceleration. All the kinematics are. So that is how we derive one of our kinematics. Now I know some of you are saying, that looks a little bit different. Okay, let's break the delta x apart. X final is equal to x initial plus VIT plus 1/2 AT squared. We just take the delta x and separate. Delta x is XF minus XI. Add the XI to both sides. Boom, there you go. Okay? And that's how we come about that equation. Okay? By the area of a rectangle and the area, adding together the area of a rectangle and the area of a right triangle. Because you can take that graph and slice up the area underneath that graph, underneath that line, into two parts. And that's how we get this kinematic. Okay? All right, now, what about another kinematic? All right? Well, one in particular, I've already shown you this one in class. If we take this equation right here, our average velocity, our average acceleration, is equal to V final minus V initial over delta T, and solve for V final, well then V final is what? Well, it becomes the initial velocity plus the acceleration times the time. So there's another kinematic. Just from this equation right here, just by algebraically solving it. solving for V final. Okay? Okay? All right. Then we have another equation where we can take our graph and look at it a little bit differently. We take our graph, velocity versus time, and we have an initial velocity here and a final velocity there. Okay, y'all. What is this area? What is this right here? What is that particular shape? Well, that is a trapezoid. And by the definition, and does it meet the definition of a trapezoid? Well, it's a quadrilateral that only has two sides that are parallel. So yes, it does. We have this side that's parallel to this side. Okay? And the definition or the formula for the trapezoid or the area of a trapezoid is equal to A side plus B side divided by 2 or times 1/2 times what? The height. Okay? So let's look at our trapezoid and see if we can come up with another equation. Well, we most certainly can. Okay? Well, if you recall, when we did this right here, the area of a rectangle is what? Well, the length times the width. Okay? So V initial times T is delta X. So delta X is equal to, now let's plug in the area of a trapezoid equation. Well, let's see. We've got side A, which is VF, side B, I'm going to call this A, and I'm going to call this B, and I'm going to call this the height. VF plus VI divided by 2, and our height is delta T. And so there's another kinematic that is very useful. Okay. And that is really the average velocity. Okay. If you look at this right here, if you look at that right there, that's really the average velocity. That's what that is. Okay. All right. And speaking of that, how can we find the average velocity? Well, here's another kinematic, and this is not in your book, but we can add it. The average velocity can also be found this way. If we take the final velocity plus the initial velocity and divide it by 2, we can get the average velocity. That's just from simply taking averages, okay? And you can graphically derive it, okay? All right, now, what about our last kinematic, the V squared one? VF squared and VI squared one. Okay. All right. Well, we know that delta X is equal to VF plus VI over 2 times delta T, isn't it? Okay. Now remember, we're dealing with constant acceleration. So if we go back to our acceleration equation, and solve for delta T, and then we're going to do what? We are going to do a substitution. Okay? So let's do that. Let's do a substitution. So let's substitute this for that. Multiply them through. And what do we get? We get Vf squared minus Vi squared. Okay? All right? All right, now, so Vf squared minus Vi squared, whoop, I'm not done, am I? Over 2a. And that's all equal to what? Delta x, right? So now what we want to do is solve for V final. So V final squared would be equal to, add a Vi to both sides. Well, first of all, let's do what? Okay, let's start right here. Okay, remember this is equal to that. Let's multiply both sides by 2a. Okay. All right. And then let's add a Vi squared to both sides. And there you have it. There's your last kinematic. V final squared is equal to V initial squared plus 2a delta x. And so there's your last kinematic and how we go about deriving it. Okay? All right. Now hopefully that helps. Okay? Now let's do some more derivations. And let's use some more calculus. Or excuse me, let's use calculus. And let's do it by integration. Okay? Well, we know that constant acceleration, or that instantaneous acceleration, is equal to the limit. Of course, we know it's the limit of as the time approaches 0, and it's dv over dt. Okay? All right, well, let's take our equation, and what we want to end up doing is integrate both sides. And so let's multiply both sides by dt and integrate, okay, with respect to time on this side. I'm going to say initial, or no, excuse me, this is time, well, we can say at time 0. We'll say time at time 0. And so this becomes what? At is equal to the integral of dv. And it's d final over initial. Okay? And so now we're going to integrate it with respect to what? Well, we're going to integrate this side and this side. We integrate this one with respect to time. And it becomes what? Well, the integral of, and I'm sorry, it should be a dt, my bad. There we go, a dt. So when we integrate it, it becomes what? At time final times 0 is equal to, well, the integral of dv is what? V, isn't it? So it's v, and of course we got final velocity and initial velocity, right? All right, now, okay? So let's set this up and do our integration. We got a at any given time, 1, 2, 3, whatever seconds, minus a at 0, which is 0, is equal to what? V final minus V initial. And so notice what we have. We have our kinematic V final is equal to V initial plus AT. So there's one of our kinematics from integration. Okay? All right, now, Let's take it a step further. Let's take that same equation. Uh-oh, I want to add some more slides. Okay. Thought I added enough, but I didn't. And so let's take that equation, V final is equal to V initial plus AT. And now let's take the derivative of velocity. Let's break that down. And what is the, how do we get velocity by taking derivatives? Well, it's the derivative, it's dx over dt, right? That's how we find velocity, right? Dx over dt, right? Okay, is equal to Vi plus At. And so let's multiply both sides by dt and get dx is equal to Vi plus At dt. And now let's integrate both sides. So we're going to take the integral, final and initial, and the integral, and notice we're going to integrate it with respect to time, and then time 0. We're going to put this in parentheses because we're integrating it with respect to time. And so when we take that integration, the integral of dx is what? Well, it's x, isn't it? So it's x final and initial is equal to, all right, now notice what happens here. When we integrate this with respect to time, it becomes what? VIT plus AT squared over 2. And then, of course, at any given time, that's your final time, and of course time at 0. And so now let's solve for this. Let's go ahead and work it out. And so we go ahead and plug in our known values. X final minus X initial is equal to what? Well, t at 0 is 0. So we don't really have anything at 0. So let's do it for t. Well, it's VIT plus, let's move this to a 1/2, AT squared. And then, of course, minus 0 because of the 0 there on your integration, okay? And so look at what we come up with. We come up with this kinematic. X final is equal to, add xi to both sides, x initial plus VIT plus 1/2 AT squared. Okay? And so there's that kinematic from integration. Okay? All right. Hope this is making sense. And now let's do one more. All right, remember, these are all constant acceleration. And if we recall, how do we find acceleration? Well, acceleration, if we take the derivative of velocity with respect to time, that's how we find acceleration. Well, we can actually take this equation and break it apart a little bit more. Okay, and let's look at it this way. What if we take the derivative? All right, we know that velocity is the derivative of taking the derivative of displacement, first order derivative with respect to time, and that's with displacement. But what about velocity? We can take velocity and say dv dx, and you say, well, why can we do that? Well, because if you think about it, not only is acceleration the rate of changing velocity, but it's also changing position. Okay? Because what is velocity? Velocity is the rate of changing position. Remember? Remember, velocity is dx over dt. So what is acceleration? Well, in a sense, acceleration can also be looked at as the rate of changing displacement. Okay? Because velocity is the rate of changing position. And so if you're changing displacement with velocity, well, guess what? If you're accelerating, you're also changing displacement there too. Okay? And so therefore, that's why we can do that little crazy looking little manipulation there. Okay? And so what we wind up doing here, we know that dx dt is velocity. So acceleration, dx over dt, is velocity dv dx. Because what are we trying to do here? We're trying to get rid of the time component and look at it with respect to displacement instead of with respect to time. Okay? And yes, we can do that. Okay? Because you say, well, where did that come from? Well, right here, which is right there. Okay? Okay. All right? And so now let's multiply both sides by dx. So we got a dx is equal to v dv. And then we're going to integrate it, final and initial, and final and initial. Okay, so when we integrate both sides, what do we end up getting? Well, if we integrate with respect to velocity, look what we get. We get a x, because what is the integral of dx? X. Okay? All right, the integral of dx is x. Final over initial is equal to, all right, if we were to integrate v with respect to dv, and you say, well, why don't we integrate a with respect to dx? Well, because we're not. We're going to integrate v with respect to dv. Okay? Because what are we trying to get to? We're trying to get to a final velocity. That's the purpose of this, okay? And so the integral of dx is x. The integral of v with respect to dv is what? Well, it is v over 2, excuse me, v squared over 2, v final over initial. Well, I didn't have to put the final, but I did, the v. Final over initial. Okay? All right, so now let's just plug everything in and let's see what we have. We have ax final minus ax initial is equal to 1/2 v squared final minus 1/2 v squared initial. Okay? So what we can do then, notice we've got two terms that are the same. Ax is ax. Okay? Ax is ax. All right? So we have then what? This becomes 2ax, or excuse me, we have, hang on a minute, I didn't mean ax. A is a, so we have two a's, so 2a. And what is x final minus x initial? Well, it's negative, isn't it? Or it's delta x. Is equal to, excuse me. Oops, back up. I'm not doing my math right. That's incorrect. Okay. I'm losing my mind. Okay. Okay. All right, so now let's consolidate this and solve for v final. Okay. Well, we can factor out 1/2 on the other side and multiply both sides by 2. And what do we wind up with? We wind up with 2. There we go. Sorry about that, y'all. Ooh, long day. 2a delta x, because x final minus x initial, okay, all right, is equal to v final squared minus v initial squared. Or we can say this, v final squared is equal to, if we add a vi to both sides, v initial squared plus 2a delta x. Okay? All right. Okay. And there we have it. All right? And there's your last kinematic. So hopefully this will help you and help you to understand how we can derive these algebraically, graphically, and through integration.